This is problem set 8. We're going to start talking about atomic spectra and the Bohr model of the atom. Get rid of those lines. All right, so let's first talk a little bit about the Bohr model of the atom. Bohr model of the atom says we have a nucleus, and then we have different levels around the nucleus, quantized levels where the electrons can exist. Okay, so I could have an electron right here. Okay, these levels we call n levels. So this is n equals 1, n equals 2, n equals 3. And each of these levels has a certain amount of energy associated with them, and we can calculate that energy. We're going to do that. But what really starts to get interesting is when we calculate the transition, or the difference between two levels, the energy of two levels. And the reason this becomes interesting is because let's say I've got an electron in this n equals 1 level, and I want to get it up to the n equals 3 level. Well, what that means, or the way to do that, is to take a photon that has a certain amount of energy. In fact, that has exactly that amount of energy in the photon. And an electron can absorb that photon and can be excited up to n equals 3. Why is this important? Well, because different atoms have different energies of their n levels, and as a result, we can look at what photons are required to excite electrons and identify atoms that way. We actually identify them more by their emission spectrums, would be an electron absorbing a photon. But if that electron then relaxed from 3 down to 1, well, that energy's got to go somewhere, and it would then be emitted as a photon. And that photon, again, would have the exact same energy as that change in energy in the electron. And so we could look at that photon and be like, oh, what energy is that? What color? What is the emission spectrum from a given atom? And we can actually use that as like a fingerprint for the atom, an identifying characteristic. So that's what we're going to start calculating now, is these different types of things associated with this model. So our understanding of the hydrogen atom will help us learn about atoms with more electrons. The n equals 1 energy level of the H atom has that much energy. What's the energy of n equals 5 level? Well, the equation that we use, the energy of n level is negative z squared times RH hc over n squared. So let's talk about each of these things. We know that c is the speed of light. We know h is Planck's constant. N refers to the n level, so they give us n. And then RH is a new constant that we haven't used before. That's a Rydberg constant. And the Rydberg constant is equal to, it is 1.0974 times 10 to the 7 inverse meters. So there's just another constant in there. Z is the atomic number of the atom that we're talking about. Now, this Bohr model and the calculations we're going to be doing today only work for single electron systems. And that's why most of what we're going to be doing is with hydrogen, because it has 1 proton and 1 electron. But in theory, this would also work with helium plus, which would have 1 electron and 2 protons. It would work with lithium 2 plus, which would have 1 electron and 3 protons. But in general, that's when we use it. So because most of the time we're using hydrogen, what is the atomic number for hydrogen? It's 1, and as a result, 1 squared is just 1, and so that usually just falls away. So if I just want to find the energy of the n equals 5 level, I would have negative RH hc over 5 squared. When I do that, I get negative 8.72 times 10 to the negative 20 joules. So jumping back over here, we're saying that if we had an electron, not in 1, not in 2, not in 3, that's bad, not in 4, but in 5, that electron would have an energy of negative 8.72 times 10 to the negative 20. Let's talk about what we mean by that negative. So we know that as an electron falls closer to the nucleus, it's going lower in energy. Why do we know that? Well, it emits a photon, so it must be losing energy. And we say that an electron has 0 energy when it's way completely dissociated from the atom. So if 0 is way out here and coming closer to the nucleus is going down in energy, that means that really any n level is going to have a negative energy. And you can see that in the equation. You're always going to have a negative value there. But that's the energy of the n equals 5 level. Now, what if we wanted to figure out the wavelength and frequency of a photon emitted when an electron jumps down from n equals 5 to n equals 1? Well, then we'd be saying we want to get this value right here, the change between 5 and 1. Well, we know how to calculate the energy of 5, we already did that, and we know how to calculate the energy of 1, so that drop is just going to be the difference between those two energies. So if I want to go from 5 to 1, I would just say the change in energy from 5 to 1 is going to be energy of 1 minus energy of 5, which is going to be negative RHHC over 1 squared minus negative RHHC over 5 squared. And I'm actually going to replace these 5's with just n for a second, because I'm going to show how this equation can simplify. We have all of these constants that exist in both terms, and so we can pull those out. RHHC, and the result is we get, because we have two negatives here, we get a positive 1 over n5 squared, 1 over n5 squared, minus 1 over n1 squared. And usually we just say 1 over n, I'm just going to say n1 and n2. And so now we have this equation that calculates the change in energy between two different n levels, and we can just use this instead of having to calculate the two n levels energies and subtract them. Now, a lot of people will ask, well, which n goes first? Is it final minus initial, or bigger minus smaller, or what? And usually my response is it really doesn't matter, because if you accidentally flip them, all it's going to do is flip the sign on your answer, and you should be able to look at the problem and know what the sign on your answer should be. Okay, so if an electron is going from 1 to 5, did it gain or lose energy? It gained, so the change in energy of the electron would be positive. If it's going from 5 to 1, it's losing energy, so our change in energy should be negative. Now this is asking for wavelength and frequency. So one way to solve this problem would be to plug in our 5, plug in our 1, calculate our delta E, and then we have equations that relate energy to frequency, energy to wavelength, wavelength to frequency. And so if we can get the change in energy, that's the change in energy of the electron. But remember, when that electron changes energy, it releases a photon. Okay, and that photon has the exact same energy as the electron change. And so if we get that electron change energy, we know the energy of the photon, and we can calculate the wavelength and frequency. That's one way to solve this problem. I guess that's the way to solve this problem. But it's important to know that there's another equation that you'll often see, and that's actually called the Rydberg equation, named after the same guy who has the constant. And that's this: 1 over the wavelength equals RH over 1 over n1 squared minus 1 over n2 squared. Okay. It's important to recognize that these are not different equations. So if I have the Rydberg equation, and let's say that I multiply both sides by HC. Okay, I haven't changed anything because I multiplied both sides by the same thing. Well, what is HC over lambda? HC over lambda, that's energy. So that is energy. So these now become the exact same equation. So recognizing that's important, but it's also important to know the Rydberg equation on its own. Okay, and that is on your equation sheet. But what the Rydberg equation is now calculating is not the energy of the photon with the transition, it is the wavelength of the photon associated with that transition. But again, once I get the wavelength, I can get energy, I can get frequency, I can get whatever I want. So I am typically going to start with this equation because it's kind of the more traditional approach. So I'm trying to get the wavelength and the frequency between, so 1 over wavelength equals RH. 1 over 5 squared minus 1 over 1 squared. Plug that into my calculator. When I do that, I get a wavelength equal to negative 9.49 times 10 to the negative 8. Now remember, I said at the end of the day, you've got to check to make sure your sign is correct. Well, I'm calculating a wavelength. Should it be negative? No, it's a length. Lengths aren't negative, and as a result, I just need to make it positive. So I just subtract, or I just erase the negative sign, and now I have my wavelength. And now with that wavelength, I know that the frequency is c over wavelength. So when I do c divided by that answer, I get that the frequency equals 3.16 times 10 to the 15 hertz. So again, multiple ways to kind of think about this problem. I generally start with the Rydberg equation to get the wavelength, but you could also start with change in energy equation and use that change in energy to get the wavelength. All right, use the Bohr equation to calculate the energy difference between quantized adjacent n levels in the hydrogen atom. As shown on the table below, what pattern can you see? Okay, so I'm trying to get transition energies. I showed you how to use the Rydberg equation to get wavelength, and I could use that wavelength, that frequency, to get an energy. And that's how I could solve this. But now I'm going to use this equation just for diversity. Okay, so for this first one, again, I'm not even taking any concern for which ends I put first and which ends I put second. I do that, I got a positive 4.90 times 10 to the negative 20 joules. Should it be positive or negative? Well, what's happening? It's going from 4 to 5, it's going up. To do that, you need to add energy, so it should be positive. Second one, this one I got 1.06 times 10 to the negative 19 joules. Again, that should be positive. Third one. And I get 3.03 times 10 to the negative 19 joules. And lastly, and again, all these are going up, so they should all be positive. And if I flip the ends, it's going to give me the exact same number, but negative, and then at the end of the day, I can just check and make sure the sign is correct. So that's 18. Gives me 1.63 times 10 to the negative 18 joules. Okay, so then it asks an important question. What pattern can you see in the magnitudes of energy changes between the adjacent quantum levels? So it's saying, I go from 1 to 2, and it requires this much energy to do that. 1.63 times 10 to the negative 18. But then to go from 2 to 3, it requires substantially less, almost a whole order of magnitude less energy. So that jump is smaller. And then that goes to n equals 3. And then to go from 3 to 4, guess what? That jump gets cut almost to a third of what it was before. It gets even smaller. And the next jump, even smaller than that. So it's an important thing to recognize that in the Bohr model, I didn't draw it well up here, but in reality, in the Bohr model, the n levels get closer and closer together the further and further you move out. And so B here asks you to draw an energy level diagram expressing, or a picture representing the energy levels of a hydrogen atom with relative spacing from n to 5. So I could say 1. That's going to be bad. I'm going to do this. If this is my nucleus, I've got 1, I've got 2, 3, 4, 5. Put an electron to show H atom in an excited state. Ground state would be putting in n equals 1, so I'll just put in n equals 2. You can put it anywhere other than n equals 1 and be correct. All right, number 3, indicate which of the following transitions require absorption of energy or emission of energy. All right, so I've got my 1, 2, 3. Again, they should be getting closer, but they're not. It's fine. I'm going from 3 down to 1. Well, that electron's going down in energy, so that energy has to go somewhere. It's going to be emitted in a photon. For this second one, I'm going from 2 up to 4. Well, that electron went up in energy. Energy's got to go from somewhere, or come from somewhere. In this case, it comes from a photon, so that photon's being absorbed. Hopefully that makes sense. If I'm going up, I'm being absorbed, or absorbing a photon. If I'm going down, I'm emitting one. All right, which of the following transitions in the hydrogen atom would result in the emission of a photon with the longest wavelength? All right, longest wavelength. And we know that energy equals hc over lambda. So the longest wavelength, because wavelengths on the bottom will be the lowest energy. We're looking for the smallest energy transition. Well, 1 to 2. Oh, and also it says emission. If I'm emitting, that means I have to be going down. So 1 to 2 is automatically out. 1 to 4 is automatically out, because those would be absorption. So if I were to draw this at n equals 1, equals 2, n equals 3, n equals 4. So what's the lowest energy to give us longest wavelength? 3 to 1. Do it in black. 3 to 1. 2 to 1. Or 4 to 3. Hopefully by this picture it's pretty obvious. 4 to 3 is far and away the smallest energy change, which means the photon emitted would have the longest wavelength. So, a couple more intuition questions here on number 4. The arrows A, B, and C in the figure on the right show 3 transitions among the n equals 3, 4, 5 energy levels in a single electron ion. Okay, A, B, and C. Assuming that they're accompanied with the loss of gain electromagnetic radiation, meaning these transitions emit photons. Do the arrows depict absorption or emission? Well, emission, why? Well, they're going down, they're losing energy, the energy has to go somewhere, it leaves in a photon. Spectral lines of the transitions are in order of increasing wavelength 80, 117, 253 nanometers, which wavelength goes with which arrow? Well, we just talked about higher wavelength is lower energy, so the highest wavelength here is going to be the lowest drop, so that's going to be A. The lowest wavelength will be the highest drop, which will be C, which means this middle one will be the medium drop, which will be B. All right, a photon of what frequency and energy would be required to excite hydrogen's atom's lone electron from 2 to 4? All right, I'm going to start with the Rydberg equation. We're doing a transition, so I'm going to use the Rydberg equation. All right, so 1 over the wavelength is the Rydberg constant. It's 1 over 2 squared minus 1 over 4 squared. And plug that all into my calculator. Now when I say plug this into my calculator, what I'm doing is I'm solving all of this, and so I get 1 over wavelength equals some number x. And then if I multiply by wavelength, I get 1 equals x times wavelength, and then I can divide by x. 1 over x equals the wavelength. So I find all of this stuff, that's my x, and I do 1 divided by that to give me my wavelength. And in this case, I get a wavelength of 4.86 times 10 to the negative 7 meters. I have to ask myself, does that sign make sense? Well, it's a wavelength, so it needs to be positive. But I want the frequency and energy, so then I would just say, I know frequency is c over wavelength. So if I do c divided by that answer, I should get a frequency of 6.2 times 10 to the 14 hertz. Awesome. I also want energy. I know that energy equals h nu, which is h times 6.2 times 10 to the 14 hertz. And that gives me an energy of 4.1 times 10 to the negative 19 joules. So hopefully you recognize it's a really small amount of energy, but I'm making a really small jump in an atom, so it should be small. How much energy would it take to remove the electron in the H atom if it was in the n equals 2 level? So we're saying we're in n equals 2, we've got all these other levels out here, and we want to remove it completely. Well, now I'm going to solve this problem similarly, but I'm going to use the delta E equation, okay, which is RHHC 1 over n squared minus 1 over n squared. Well, what is my final n here? My final n is removed, which is as far away as you can get, which is infinity. So what I'm going to do is I'm going to say delta E equals RH, HC 1 over 2 squared minus 1 over infinity squared. What is 1 over infinity squared? Well, if I'm dividing by the biggest number possible, my result is going to be the smallest number possible, which is just 0. That just goes away, and I'm left with maybe you'll recognize this looks just like the equation that we used at the beginning. Okay. And that's because being infinitely far away is 0 energy. So if I'm calculating the energy change between here and 0 energy, it's just going to be equal to the energy of that n level. So I'll plug that all in my calculator. 1 over 2 squared times RH HC. I get a delta E equal to 5.45 times 10 to the negative 19 joules. Should be positive or negative. Well, I'm kicking it out. If I want to remove it, I've got to add energy. There we go. Okay, the energies of photons emitted by 1 electron atoms and ions fit this equation. Okay, don't be confused. This is not a new equation. If I multiply RH by H by C, it equals 2.18 times 10 to the negative 18. All they've done is they've multiplied these constants together for you. Not a new equation. Same thing you've always been seeing. And Z, for most cases, is 1 because we're dealing with hydrogen. The energy of photons emitted by 1 electron atoms and ions fit this equation. Where Z is atomic number, okay, we know these things. They tell us specifically N2 is greater than N1. Again, if you flip them, you just get the opposite sign. Is the emission associated with N2 to N1 transition in a 1 electron ion ever in the visible region? Why are we not? Well, let's see. If I do, and I'm actually going to ignore this equation because I know it's just the same as the one I've been using, and I'm just going to use wavelength because I know the visible region for wavelength. When I do that, I get a wavelength of 1.21 times 10 to the negative 7 meters, which is 121 nanometers. So is that transition in the visible range? No, because again, visible is about 400 nanometers to 750 nanometers. That's not in that range. But is it ever? Well, what could change here? What could change is Z, right? I said this is for hydrogen, but it could be for helium plus, which would have a Z of 2, and it could be for lithium 2 plus, which would have a Z of 3. Well, if I increase Z, what does it do to the energy? Increases the energy, which would do what to the wavelength? If I increase the energy, I'm going to decrease the wavelength, which means 121 is the highest it could ever be. If I increase Z, 121 is going to go lower, so it's never going to be in the visible range. So you're never going to see a transition between n equals 1 and n equals 2. Balmer observed a hydrogen emission line from 6 to 2, but not from 7 to 2. Why? Well, often people think, oh, because hydrogen only goes up to n equals 6. That's not true. That's the wrong answer. But if we do 1 over wavelength equals RH, 1 over 7 squared minus 1 over 2 squared, we get a wavelength of 397 nanometers. Is that in the visible region? It's just outside, which is why Balmer did not observe it, because it was not visible, or not in the visible range. That would have been a little bit higher energy, so that would be about, that would be right in the ultraviolet range, which is why I didn't see it. All right. Which following diagrams show the emission spectrum and absorption spectra in the visible region for hydrogen gas? Which is emission, which is absorption? So emission has fewer lines on it. You can kind of see these lines are associated with drops in energy level, or with drops in the Bohr model, and we know the Bohr model energy levels get closer and closer together, which is why these become closer and closer together. Perfect representation of that. This is emission, which means the same, remember this, when an electron can fall and emit a photon, that same energy is what is absorbed to excite an electron. So if we were to shine light through hydrogen, these colors would be absorbed to excite electrons, which is why this is the absorption spectrum. All of the rest of this stuff would go right through, and we could see it behind, like if we shined it through hydrogen gas, we would see all the rest of this after the light goes through hydrogen gas. Whereas these colors are absorbed, and then if we were to give it a second and let it absorb, or let it emit energy on its own, it would emit those wavelengths after those electrons relaxed. The wavelengths of the 4 lines in the visible region of the electromagnetic spectrum are given. So these ones we've got wavelengths. Describe the transition producing the line at 656 in both spectra. What energy levels are involved, whether a photon is being absorbed or emitted. So we know that our wavelength, 656 times 10 to the negative 9. I'm trying to figure out the n levels to produce that. I'm going to cheat a little bit here. I know that 2 to 1 is not visible. And so the fact that we can see this line means it's not finishing at 1, because 2 to 1 is not visible, and anything higher energy than that, 3 to 1, 4 to 1, is just going to be a lower wavelength, a lower wavelength than this, so less visible. So I'm going to start guessing with n equals 2 and see if that works. So I'm going to say 1 over my wavelength equals RH times 1 over 2 squared minus 1 over something. In this case, I had to make sure that my signs actually are correct. Yeah, this will work. 1 over n squared. So I'm going to see if I can get a nice clean number for n here. And if I get a nice clean number, then I know it was falling from that to 2. So 1 over 66 times 10 to the negative 9. I'm going to divide RH to the other side. And I, just to give you an intermediate step here, got 0.1389 equals 1 over 4 minus 1 over n squared. So if I do 1 4 minus that, I get 1 over n squared equals 0.11109. So 1 over 0.11109 gives me n squared equals 9, which means n equals 3. So this is dropping from 3 to 2. That's how I got this energy, or this wavelength. Which makes sense, right? Because higher energy drops, so 4 to 2, 5 to 2, 6 to 2, will give me lower wavelengths. And these are higher energy colors as well. All right, the hydrogen atomic emission spectrum includes a UV line with a wavelength of 92.3. Is that line associated with the transition between different excited states, or between an excited state and the ground state? Well, what is ground state? Ground state is n equals 1 for hydrogen. And so in order to see if it's between two excited states or between a ground state and an excited state, I could just say, let's pretend it's the ground state. And then I would have my wavelength, and I would have one of my n's. When I calculate the other n, if I get a nice clean number, then I know that it was actually the ground state. If I get something funky that's not an integer, then I know, okay, so n1 is not real. It must be between excited states. So I would say 1 over 92.3 times 10 to the negative 9 equals RH, 1 over 1 squared minus 1 over n squared. 0.98726 equals 1 over 1 minus 1 over n squared. And I get 1 over n squared equals 0.01273. So 1 over that answer. So I get 78.518 equals n squared. Take the square root of that number. Oh, that's pretty funky. But I think the actual answer is that you should get about n equals 9. That's kind of a stretch because the actual what you get is 8.86, but I guess it's close enough to say that n equals 9. So the actual answer is from an excited state and a ground state. Yeah, kind of messy there, but I guess close enough. All right, astronomers have detected hydrogen atoms in interstellar space with n equals 732. Why is it in space that they can get out that far? Well, it's because in space there aren't a lot of other atoms for those electrons to get attracted to when they get that so far away from their own nucleus. Suppose an atom in that excited state undergoes a transition from 732 to 731. How much energy does it lose? So I'm going to use my Rydberg equation. I could also use my delta E equation. 1 over 732 squared minus 1 over 731 squared. Let's see. That gives me a wavelength. I got negative 17.83 meters, but it's a wavelength, so it should be positive. Okay, but it doesn't want wavelength, it wants the energy. Well, I know energy equals hc over wavelength. When I do that, I get a an energy of 1.114 times 10 to the negative 26. Now the question is, should it be positive or negative? Well, it's going from 732 to 731. It's going down, so it should be negative. So my change in energy equals negative. That guy, joules. What is the wavelength of the radiation? Awesome, we already found it. Wavelength is 17.83 meters. And then what kind of telescope would an astronomer need to detect this radiation of the wavelength? Well, 17.83 meters is in radio. is in the radio spectrum. So that's what we would need. And that takes us to the end of this problem set about the atomic spectra and the Bohr model. Hopefully this gave you a little bit of understanding, a little bit better of understanding of the usefulness of light when trying to learn about atoms.